All right, continuing on with fun with formulas. You're going to get some more formulas thrown at you in this lesson. So, such as these guys, these are called our double angle formulas. And you'll see in a minute here how we're going to be using those. But one of the things I really like to show you is where these formulas come from and how they were figured out. One of the things you can do, because there's a lot of formulas this chapter, but one of the things you can do instead of memorizing all of them is simply learn how to use formulas that you already know in order to produce formulas that you don't know. So I showed you guys how to do that when we derived the Pythagorean theorem identities at the start of this chapter, right? We used the sine squared plus cosine squared equals 1 formula in order to find two other formulas, right? And so we wouldn't have to memorize all three of them. I would only need to know the first one, and then I could use the process for deriving the other two. So we're going to do the same thing on this one. Of course, you always have the option of just memorizing formulas, and that's fine. But if you like the idea of learning how to get them rather than memorize them, then follow along with this one. So the sine of 2 theta, this is our double angle formula, could be written as the sine of theta plus theta. Right? Because theta plus theta would be 2 theta. So, but by writing it this way, now I've turned it into a sine sum formula, right? Which is what we learned in our last lesson. So we learned that the sine of two values being added together is simply the sine of the first one times the cosine of the second one plus the cosine of the first one times the sine of the second one. So if you look at what we just wrote now, though, is these are identical, right? This is sine cosine. This is also sine cosine because I can flip that order. It's just multiplication. And so basically I'm adding this plus itself. So it simply becomes 2 sine cosine. And this is our double angle formula for the sine value. And so again, I could just memorize this right here, that the sine of 2 theta is 2 sine cosine. So I can memorize that, or I can just understand how to get it by deriving it from the sine formula. Let me just take you to this page real quick on 421 so you can see some of this. So here's the one that we just came up with, the 2 sine cosine value. When you do the cosine of 2 of a double angle formula, there's actually 3 different ways you could write this, and I'll show you that, how you could get those. And then same thing with tangent. So these are the formulas. So again, if you can just refer to page 421, you'll have your list of double angle formulas right there in front of you. Let me at least show you one more here. We don't need to take up too much time with this, but again, let me show you how we could derive this guy. And I think you're going to get the idea for how you could do this one as well. But as I do the cosine of 2 theta, again, that is simply the cosine of theta plus theta. And in our last lesson, we learned how to do the sum of a cosine formula, right? It was simply cosine cosine minus sine sine. So I'm going to say cosine cosine minus sine sine. Okay, and so if I wanted to simplify that, obviously that is simply cosine squared minus sine squared. And so that is one of our formulas for the cosine of 2 theta. So we could write it this way. The reason there are 3 formulas for this is because I could replace either one of those by using my Pythag identity. So remember we got this identity that sine squared plus cosine squared equals 1, which means I could replace cosine squared with 1 minus sine squared. So it would look like this. Let me see if I can find room for it. So here's one of them. But if I replace cosine squared with 1 minus sine squared, then I get 1 minus sine squared minus sine squared. which is just 1 minus 2 sine squared theta. And so there's one of the other formulas. And then I can do the same thing by going back to this one. And now if I replace sine squared with 1 minus cosine squared, so on this one, I'm rewriting this, but I'm going to replace sine squared with 1 minus cosine squared. So it looks like this. I do have to remember to include those parentheses where I subbed in for sine squared, because otherwise this would not come out the same. But basically on this one, if I simplify this, I'm now looking at a negative 1 right there. I'm looking at a positive 2 cosine squared. So I can write this as 2 cosine squared minus 1. So that's why we end up with 3 formulas for the cosine of a double angle, right? Which is these guys right here. Those are the ones we just came up with. Again, it's a lot to memorize. Personally, I've always found it kind of nice to know just simply how to get them. And so I can just memorize only a couple formulas and then just understand what needs to get subbed in order to find the other ones. So those are the 3 cosine formulas, and then I'll show you real quick the tangent of a double angle. I'm going to do this the same process. I'm going to see this as tangent of theta plus theta. So I'm just taking the exact same process that I did on the other guys. So I'm going to sub in the sum formula for the tangents, which we saw in the last lesson. So on top, I'm looking at, let's see, tangent of the first one plus tangent of the second one over 1 minus tangent tangent. So it looks like this. So now if I clean that up, on top is simply 2 tan theta and all that would be over 1 minus tangent squared theta. And that's it. So there's our tangent formula. Again, we can see that right here on your book. So that's where those guys come from. So those formulas are simply derived from other formulas. Right? That's all these are. So again, you could memorize them. If you just choose to memorize them, that's fine. If you want to know the process for how to get them, there you go. So we're going to go through using some of those ideas to prove some stuff. So we're going to prove that the cosine of 6x is equal to this. So right off the bat, we are seeing this angle get repeated. So in other words, I have the cosine. So remember, we're taking the side that's more complex, and we're going to simplify this. And hopefully, if we do this right, it comes out looking like this. We know that cosine squared of 3x is the same thing as cosine of 3x times cosine 3x. I'm going to do the same thing with my sine values. So sine 3x times sine 3x. All right, so obviously if we're noticing this, looks just like our cosine formula, where we were just adding 2 angles together. So remember, this is like cosine of u plus v is equal to cosine u, cosine v minus sine u, sine v, right? That was our cosine formula from the previous lesson. So we can now mold it back into the cosine of a sum of 2 angles. And obviously if we add those 2 angles together, I'm now looking at the cosine of 6x, which matches the left side, so we have our proof. So we have some other identities here to take a look at. We have something called power reducing identities. So let me show you those real quick on page 421. Those are these guys. So these are called power reducing identities. In other words, if I have a sine squared and I don't want the exponent, I want it to just be first powers and not second powers, I can reduce those powers with these formulas that I see on the right. right? So I'm going to change the sine squared into 1 minus cosine of 2u over 2, on and on and on. So these are anytime you are wanting to shrink your powers, right? Shrink those exponents. Then we can use these formulas right here. So I'm going to give you one that looks like this. So again, I want to take the side that's more complicated and simplify it to look like this guy right here. So we have the cosine of theta to the 4th power minus sine theta to the 4th power. So if you look at our cosine formula, which is this one, so we're going to be able to write that as 1 plus cosine 2u over 2. All right, so for this first part, just the cosine to the 4th, if I put it into this model, notice in the original, when you had, it was cosine squared that equaled this, right? So if I really want to fit the formula, I really need to see this as cosine squared, not cosine to the 4th. And the same is going to be true with him. So let me rewrite that guy. So this is simply going to be cosine squared of theta squared. Right, that would be the same thing as cosine to the 4th. Do the same thing with my sine function. So it looks like this. So now I can sub in this in place of cosine squared. So now I have 1 plus cosine 2. We're going to write the angle as theta because that's what they're using on this problem. So I'm going to say 1 plus cosine 2 theta over 2. And let's do the same thing with our sine function. So sine squared of theta can be rewritten as 1 minus cosine 2 theta over 2. Quantity squared. Okay, so now we have at least reduced our powers. We're now down to function squared. To go a little simpler with those, we're simply going to need to do some foiling here. So I'm actually going to have to multiply this by itself. I'm going to have to multiply this by itself. So let me show you what that would look like. I'm trying to squeeze in what little room I have right now, but if I FOIL the top, it's going to be, let's see, 1 plus 2 cosine 2 theta plus cosine squared 2 theta. All that's going to be over 4. Let's do the same thing on this one. Again, I'm going to square the top. So I'm going to get 1 minus 2 cosine 2 theta plus cosine squared theta, 2 theta. All that is going to be over 4 as well. Do keep in mind the subtraction in between does apply to everything behind it. So really I could do the whole add a line, change the sign thing, and that might make this a little more clear. In fact, let me just do that. So this is going to become a negative 1. This will become a positive 2 cosine 2 theta, and that plus would change to a minus. If I can get my whiteout to work, it will. There we go. So that plus is turning to a minus. So I just distributed the negative basically. So now you can see kind of what happens here. These are common denominators, so I can go ahead and combine what's on top. My 1's cancel. My cosine squareds cancel because one's positive, one's negative. All I am left with is a positive 4 cosine 2 theta over 4. And of course my 4's at this point could cancel, and I'm left with just the cosine of 2 theta, which is what we were trying to prove. So that was a tough one. A lot of side work that went into that, but one of the ways we can do those things. So what if we wanted to say, let's rewrite the cosine to the 4th of x with no powers greater than 1. So in other words, I just need to simplify this all the way down until I no longer have exponents, right? Because I only want powers greater than 1. So we'd start out with the same trick that we used from up above. Right, first of all, I want to see this as simply cosine squared of x squared. So that reduces me already down to just cosine squareds. We know that cosine squared of x can be reduced, as we saw right up here. So when we had the cosine squared, we were able to sub in this formula. So I'm going to do the same thing on this one. So I'm going to replace this with the power reducing formula of 1 plus cosine 2x all over 2, and that is still a quantity squared. So we're not there yet because remember, I want no powers greater than 1, so I got to keep shrinking this guy down. So I'm going to do the same thing I did up above. I'm going to FOIL. See what that gives us. It's going to be this line that you saw right here. So that puts me here. So I still have a cosine squared. So again, I'm going to need to, one more time, plug in a formula for that to shrink that thing down even further. So in other words, I'm going to rewrite all of this except for this piece right here. Again, I'm going to need to sub in my power reducing formula for that piece of it. So I'm going to bring it over here. I'm trying to make sure I can get all this in. So I got my 1 plus 2 cosine 2x. But I'm going to replace this with my power reducing formula. But one thing you got to notice on this one is what the angle is right now. When you go from cosine squared to this, what happens is you multiplied your angle times 2. In other words, when I say 1 plus the cosine of 2x, right, it's like I'm multiplying my original angle times 2. So I'm multiplying my original angle of 2x times 2. So it's going to become 4x. And all of this is over 2. Still got my 4 on bottom. So we're almost there. I now have an expression where I no longer have exponents greater than 1. I just don't want to leave this as a complex fraction. So I'm going to multiply this by, because of him, I'm going to multiply this by 2 over 2. So as I distribute that through the top, I'm going to get 2 plus 4 cosine 2x. Plus, and then here's where those 2's will cancel. So plus 1 plus cosine 4x. On bottom, it's over 8. And so now I don't have a complex fraction. My powers are all less than or 1 or less, so I'm good. I would just combine like terms. So obviously the 2 and the 1 can become a 3. But other than that, that's where I would leave my answer. All right, let me move on for you. So here's some of the things on this page. So we already did this on the previous page. We already proved the double angle identities. We already did this problem on the previous page. So let me move on down here. So in our previous chapter, we started working on solving equations, solving trig equations. And so we're now using these identities that we've learned to solve equations. So here's the equation that we are starting with. Cosine of 2x equals the sine of x. They want us to find any answer within the interval from 0 to 2 pi, including 0. So here we go. So obviously we want to sub in our double angle formula for the cosine of 2x. So remember on this one, it's a little tricky because we actually had 3 formulas for the cosine of 2x. And so sometimes you have to play with them until you kind of figure out the one that gets you further. One of the things I always try to look for when I solve a trig equation is you never want more than one trig function. Like I need an equation that either only has sine or only cosine or only tangents, things like that. So that's kind of one of the goals you can always look for when you're solving a trig equation is how do I get rid of some of the other functions. Like I don't want this in terms of cosine and sine. Let's sub in something that gives us only a sine function. So what they did is they actually took an extra step on this than what we would have needed to do. If I look at my double angle formulas for the cosine of 2x, let me take you back real quick. So if I look at this one, so if I would have just gone straight to this formula right here, 1 minus 2 sine squared x, then I could have jumped down to this statement right here. This is 1 minus 2 sine squared x, right? And so I actually could have gotten this problem done a little quicker if they would have used that formula instead. Either way, what they did was they said, well, let's say that the cosine of 2x is cosine squared minus sine squared. That's one of the formulas. Then we're using another Pythag identity, which is cosine squared equals 1 minus sine squared. But now look what they've done. The goal was, let's get an equation with only sine functions in it, right? So this could now be written as 1 minus 2 sine squared theta. We're going to subtract this over to the other side. So the whole thing equals 0. And you're now just solving a quadratic. So think of this as 2x squared plus x minus 1. Right? We're just solving a basic trig equation, quadratic equation at this point. So they chose to factor it, which is what I would have done as well. You set each factor equal to 0 to get the solutions. So if I set 2 sine x minus 1 equal to 0, I get this. If I set this equal to 0, I get this. And so now I need to find all of the solutions that fit these descriptions from 0 to 2 pi. So the sine of what angle equals a half, and the sine of what angle equals negative 1. So as we look at this, so the sine of what angle equals a half? Well, that would occur right here at pi over 6. That would also occur at 5 pi over 6. So we got those. And then it also said the sine of what angle equals negative 1. Well, the only sine value that equals negative 1 is right here at 3 pi over 2. Those are the only answers we're going to keep because of the domain that they gave us. And so that's why you'll see our list of answers would be those guys right there. They did make a little typo on this. That's supposed to be a 2 right there. I should say 3 pi over 2. Just one of those new book typos that always happen. So, but that should say 3 pi over 2. All right, so let's jump down to a couple of these. So 2 things I want to show you. We're going to do number 8, which is going to be similar to what we just did. Then I will show you number 11 because I wanted to introduce you to a half angle identity. So we haven't talked about those yet. So we'll get to that one on number 11. I already have those set up for us on this next page. So on number 8, first thing I'm thinking is I don't want the sine of 2x. I want to replace that with my double angle formula. So let's look at that one real quick. So that would just be 2 sine cosine. So let's plug that one in. As I already mentioned, I really don't like having 2 different trig functions in here. It makes them very hard to solve. But in this case, it's kind of there intentionally because when we factor out the greatest common factor, then I'm separating my sines from my cosines. So I'm going to factor out 2 sine x, leaving me with just cosine x minus 1. So even though I have multiple trig functions, which is usually a bad thing, in this case it's okay because they're a part of separate factors, and all I have to do is set each factor equal to 0 to get my solutions. So I'm still solving them separately. This one, of course, if I divide the 2 over, it's still 0, so the sine of what angle equals 0. So on this one, we know that would occur at 0 and pi. So this, let me take you here. So sine of what angle is 0? So that occurs right here, and it occurs right here. So here's where it would really matter on the domain that they gave you. So if I gave you the same domain that they gave us on the previous problem, which was this, which is a pretty common domain, then I'm only going to keep the ones within that interval, which would be 0 and pi. I'm not going to keep going and call it 2 pi as a third answer because it's non-inclusive within that kind of a domain. So I know this x will happen at 0 and pi. Now, if there was no domain given like this, remember what we learned in an earlier lesson? I could add on to this plus 2n pi to each of my answers in order to show that it continues on forever. So if there's no domain given, then technically we're supposed to say plus 2n pi on each of these answers. Let's look at this one. So again, this, if I simplify, I'm saying the cosine of what angle equals 1. So on our unit circle, we know that would only occur at 0. Right, that would only occur right here. So if I just keep my domain in mind, then that would only happen at 0. Again, if this did not exist, I would have to say plus 2n pi. If this is the domain that I'm given, then 0 would be the only one that I would keep. So there's really only two answers for this, because I'm not going to repeat my answer. So I would just say my x is 0 and pi. All right, let's jump down to this one. I think we have a little bit more after this one, but we're almost there. All right, so I wanted to introduce you to a half angle formula, so let me take you to that real quick. And if memory serves me correctly, I believe it's in the back of your book where you have like a list of all these formulas on one page. If you look at like the very, very last page of your book, I'm pretty sure that's where they are. So here's our half angle formulas. They look like this. And so for the one that we're doing right now, we have the sine of x over 2. So we're going to be plugging in this information in for the sine of x over 2. So let me just write that on my paper so I have it in front of me. So square root 1 minus cosine u all over 2. Okay, let me take you back to where we were. That plus or minus does matter. You actually have to keep that. It's kind of like goes back to when you were solving equations and you took the square root of both sides of the equation. You had to throw in that plus or minus. We got to keep that for this. So those are both possible solutions. So for now, we got to keep it. So here's our steps that I'm setting out for us. So first things first, we're going to sub in our half angle formula. So I'm going to say the cosine of x is equal to -3. And so I'm going to replace the sine of x over 2 with this. Just bring down the rest. All right, so there's our substitution. Just like any basic equation, I want to isolate my radical. So one of the things I wanted to look at on this one with you is recognize what's going to happen to this. Sometimes we really have to make a decision on whether this answer is supposed to be positive or negative. In this case, when I isolate this radical, at some point, I'm going to have to square both sides. Well, when I square both sides, obviously this would turn positive. So really beyond this point, I don't need the plus or minus. I know it has to be the positive version of this formula because I'm going to end up squaring both sides. So anyway, let me keep going through with this. So I'm going to subtract my 2, divide by -3. And so that's going to equal this right here. I'm then going to square both sides to get rid of the radical. So this is just going to become 1 plus cosine x all over 2. when I square this side, so let me just write it like this for now. So we squared both sides. That got rid of the radical. So from here, we're just solving it, right? I need to sort of identify this quadratic that I'm going to be solving, and then I'm going to solve a quadratic. So let's do a little cleanup. If I square this side, so cosine of x minus 2 would become cosine squared minus 4 cosine x, I'm just foiling, plus 4, all over 9. So it looks like this. From here you could cross multiply. So I'm going to multiply my 2 over to here and my 9 over to here. So if I bring the 2 over, it becomes 2 cosine squared of x minus 8 cosine x plus 8. On the other side, I brought the 9 over, so it becomes this. And I'm just now noticing the mistake in my work that I made earlier. Somehow my minus became a plus. I'm not sure how that happened. Let me change that to a minus before we get too far. So I should have said 1 minus cosine. Alright, so now I want to get everything onto one side, make it equal 0. So we're going to say 2 cosine squared. If I add this 9 cosine over, it becomes plus 1 cosine of x. If I subtract that 9, it becomes minus 1. So we're right back to factoring. So if I factor, I get 2 cosine x minus 1 and cosine x plus 1. We're going to set each one of those equal to 0 and solve it. All right, so cosine of x equals 1/2 and negative 1. So let's take a look at how this would play out as far as these repeating values. So notice on this, what if we don't have a domain given to us and I have to find possible answers to this? So cosine of what angle is 1/2? So we know from our unit circle that would add pi over 3 as well as 5 pi over 3. So let me just write those down. So we know it's pi over 3, we know it's 5 pi over 3. And cosine of what angle is negative 1? This is the other guy that we were solving. We can see that happens right here at pi. So that was our third value. So again, if they didn't give us a specified domain for this, we're supposed to tack on to the end of this plus, I think they say 2 pi n, something like that. Basically just to show that these answers repeat every time I add 2 pi. So I could add 2 pi, 4 pi, 6 pi, and I would get repeating answers that would all fit the original equation. So that's just what we do when there's no specified domain on these guys. So almost done. Let me show you one last thing. Just want to discuss it with you. So on this one, it said cosine squared equals sine of x over 2 quantity squared. So the main thing I wanted to show you on this one was because this was a quantity squared, when they subbed in the half angle formula for the sine value, because it was that quantity squared, that squared canceled out the radical, right? And so that left them with this equation right here, and then they used some very basic algebra to continue solving. This one ends up being pretty much the same as what we just did after that. So one more thing, if you can handle, and again, notice how they're writing the answers to this, plus 2 pi n, just to show that it does continue on. So I wanted to just show you one more thing. If you can hang on for one more minute. How would I apply a half angle identity to find something like tangent of 75? So again, keep in mind, tangent of 75 is not on the unit circle. We don't see 75 degrees. So we have to somehow fit this into a different formula in order to use it. So instead of 75, what if we saw that as the tangent of 150 over 2? right? Because that's also 75, but now it's written in such a way that I could apply my tangent half-angle formula because I know 150 degrees is on the unit circle. So let's just look at it real quick, what the tangent half-angle formula looks like. Oops. I think I lost my page. Let me go back real quick. Here we go. So you do have 3 versions of this one, so we can apply whichever one makes sense for that problem. I'm just going to pick the third one here. Actually, I'm going to pick the middle one. So we're going to say 1 minus cosine over sine. So I'm going to say 1 minus cosine over sine. So knowing that those are values on our unit circle, we should be able to plug in and simplify pretty easy. So at 150, so let's see, we got cosine is negative rad 3 over 2. And on bottom, we're doing the sine value, which is 1/2. So we just need to do a little cleanup on that, and once we simplify it, that will be our answer. I'm going to use some common denominators up here. So on this one, if I just multiply everything by 2, it's going to be nice and simple solution for us, and that would be it.